Alright, so this is problem 9-1, and it says a technician uses the circuit above to test prototypes of a new battery design. The switch is closed and the technician records the current for a period of time. The curve that best fits the results is shown in the graph below. The equation for this graph is I equals I naught e negative k e to negative kt, where t is the time elapsed from the instant the switch is closed and I naught and k are constants. Using the information in the graph, determine the potential difference V naught across the resistor immediately after the switch is closed. Because it is a circuit, you may use the equation V equals IR to determine the potential difference. To find the I naught, look at the graph and determine the initial I when t equals 0. So right here, about 9.5, 9.3. Your R is given to you in the circuit above, 3.3. So you simply multiply the two values and you get 31 volts. Would the open circuit voltage of the fresh battery have less than, greater than, or equals to the value in part I? Justify your answer. It would be greater than because a real battery has internal resistance. So when it is connected to the circuit, only part of the open circuit voltage appears on the external components. Part B says, determine the value of K from this best fit curve. Show your work and be sure to include the units in your answer. Because you have a differential equation I equals I to the e to the kt, negative kt, you can solve for k by choosing a point t, comma I on the graph and plug in the I naught used in part A. ln of I equals ln of I naught ln and times ln of e to the negative kt if you ln both sides. Simplify, divide ln of I naught to both sides, and you get ln of I over I naught equals negative kt ln of e. Negative kt comes in front because of power. Solve for k. Then you pick a random point on the graph to determine k. And I chose to pick 0.5, which happened to be around 7.5, I believe. And we plug it in and solve. Got 0.4 hours to negative 1. Different following in terms of R, K, and T. The power delivered to the resistor at time 0. Because it is a circuit, we can use the equation P equals I squared R. So, when T equals 0, I equals I naught. Then P equals I naught squared times R. The power delivered to the resistor as a function of time. This time we use the given equation I equals I naught e to the negative kt for I. We plug it into P equals I squared R, and we simplify, getting P equals I naught squared R e to the negative 2 kt. The total energy delivered to the resistor from T equals 0 until the current is reduced to 0. Since total energy is the integral of power, we can use the equation U equals the integral of P dt. Limits of the integration are from 0 to infinity because the current is reduced to 0 by infinity, no matter what. So we use P from II and substitute and solve. So we get U equals the integral from 0 to infinity of I naught squared R e to the negative e to the negative 2 kt dt. We integrate and then solve, and we get U equals I naught squared R over 2k. And that is 9-1.